the second half of the morning session. As first speaker, we have John Gibbon from Imperial on Navier-Stokes equations in active and multi-phase flows.
Thank you very much. Thank you. Okay, now I see I have the graveyard slot before lunch that everybody wants me to finish slightly early so you can get off and eat. So I will do my best to get through this. Now, basically, I went to high school, as you would call it, 1960 to 1967, and therefore was one of those schoolboys who was forced to learn Latin. Okay, and, yes, a wonderful language. Okay, but forced to learn Latin, every schoolboy had to learn Latin by reading Caesar's commentaries on the Gallic War. Okay, I see some people laughing in the audience, exactly.
I have written a paper citing Caesar.
Exactly. Okay.
It's in the list of references.
Okay, and in his commentaries on the Gallic War, there were these nice little things about slaughtering Gauls by the million. Every schoolboy learnt that all Gaul is the beginning, is the opening line, all Gaul is divided into 3 parts. Okay, well actually Gaul was divided into 5 parts, but since Caesar said it was 3, it's always remained 3. Okay, so my talk is going to be divided into three parts. Okay, now before I actually discuss these things, whoops, putting this the wrong way around. Okay. Before I discuss these things, I ought to say I'm a Navier-Stokes analyst, and it's very different than most of you in this room. There's 1 or 2 of us, I see Idris at the back and Daniel and myself, but we're marooned in physicists, etc., etc. So I bring a very different perspective on things. Physicists like special solutions, they can match with experiments. Analysts like to look at global properties of equations and PDEs and see what we can. So I want to tell you what I can bring to the table from my side of the barricades, as it were. Okay, but as an analyst, it's probably too extreme to say I feel like Daniel in the Lion's Den here, but maybe I'm a mathematician trapped in a Petri dish. Okay, so let's start. My 3 parts are essentially, most of you know the Toner-Tu equations. I'm going to actually look at these from a particular perspective. My collaborators, Rahul Pandit at Indian Institute of Science, his student Kiran, and Nadia Padhan, who I think is in this room. And then a variation on Toner-Tu is in effect, the Swift-Hohenberg equations, which Edgar has very nicely set up for me in his talk, thank you, Edgar, which has anti-diffusion and then bi-Laplacian hyperdissipation. Also with Rahul, Kiran, and Daniel Boutros here, who is Idris's student in Cambridge. And though this is for the flockers and the swimmers, if you're not a flocker, but you're a phaser, as it were, then I'm going to also look at the phase field model of Cahn-Hilliard Navier-Stokes and see what I can say about that. Okay, so let's start. Oh, I should say my collaborators, also Rahul, Anupam Gupta in Hyderabad, and Nairita Pal, who was here earlier but had to go, who is in Kharagpur. So let's go. So what properties do the 2D and 3D Navier-Stokes equations enjoy? I'm doing this all in one slide. Okay, okay. So first of all, here you've got, sorry, I'm showing my age by pressing all the wrong buttons. Okay, here you've got Navier-Stokes equations. Okay, you take the curl to get the vorticity, and you get this nasty term, which we call vortex stretching. Now that guy is non-zero in 3D, but in 2 dimensions, gradients in the plane, omega is vertical, so omega dot grad is 0, and so in 2D, that term is not there, and that makes all the difference. So if you're a physicist who says, well, we just have Navier-Stokes turbulence, there's a big difference between 2D turbulence and 3D turbulence. Okay, now, what do we require? Okay, first of all, you require that, in effect, the energy, the L2 norm, is bounded. Okay, and that means solutions are attracted into a ball, in effect, in L2. So if you start somewhere in initial conditions, you're always attracted into this ball. If you start inside, you stay inside. Okay, but we want to know how smooth is this ball. And that means that you would like to have that the gradient of u, the integral squared, is finite. If it is, then this ball is compact. And if it is, and then various other technical conditions we need not go into, then we have a global attractor, which I'll call curly A of finite dimension. Okay, now for 2D Navier-Stokes, it's yes to both these properties. You have this one and you have that one, and this is for all time pointwise. Okay, not just time, we have time average for 3D, but we don't have it finite pointwise in time. But yes to both properties because that term is not there, and that makes all the difference. Now 2D Navier-Stokes, it has a cascade and it has an inverse cascade. You'd see that numerically because the inverse cascade means energy comes flowing back down to small k, that means small wave numbers, large L, it's why you get these big fat vortices. Okay, and Constant Foyesh and Timam in '87 proved that the Lyapunov dimension of this global attractor, so that's for all solutions from all smooth initial conditions, okay, they proved it's bounded by Reynolds with a log correction. Now, if you look in Landau and Lifshitz and they talk about number of degrees of freedom in a system, you could interpret the Lyapunov dimension as that. And that in effect means that if you're in 2D, it means you need Reynolds to the half in each direction, which roughly fits with a numerical computational fluid dynamicist's intuition as to how many grid points you need to resolve a flow. Yes?
So does this mean that 2D Navier-Stokes don't have anomalous anisotrophs?
Well, can we talk about that afterwards? I'd rather not go into that detail here because I'm trying to do everything in one slide. Okay, and then you've got 3D Navier-Stokes, which is yes to the first, but no in the sense that nobody has proved the second, that object is finite for every arbitrarily large time. We have the time average is bounded, but that's not the same thing. And that's the $1 million question, basically, for Navier-Stokes, that we don't have control over this thing. What we have is Lerais weak solutions, and they're known to exist in the form of time averages. A weak solution is essentially something which you can only really express as integrated against a test function. And Foyesh, Gilpin, and Timam in '81, in effect, found an infinite number of time averages or integrals, which you can, they did it in L2, I did it in L2M, but it's trivial to change. And essentially, what you get is this exponent here, 4 minus d, beloved of field theorists, 4 minus d, okay? This alpha NMD, which is here, okay? And that isn't just something dreamed up, it's actually a property of the fact that Navier-Stokes has an invariant scaling property. Okay, now you'll see all this coming up later. Okay, so let's go to Toner-Tu. Okay, well-known equations by Toner in 295 and an even more well-known paper with Sriram in 2005. Okay, nu is a standard viscosity, alpha is driving is a frequency. If you do your dimensional analysis, as I was always taught in physics, always look at dimensions. Beta basically has the dimensions of an inverse viscosity. And lambda, which I'm told is a sort of amount of push-pulling in the system, is dimensionless. Okay, and I'm going to follow Rana and Palekar who basically, whereas these guys, I think, basically had additive stochastic forcing, they discussed incompressible deterministic Toner-Tu, which is what I'm going to do. Okay, so you'll find this in this paper here. Okay, and I'm going to non-dimensionalize like all good physicists. Okay, and I was taught in all units from CGS, British units, CGS, MKS, SI, all the way through the 1960s, 70s, 80s, so I don't understand any of them because I get mixed up. Okay, so I'm very happy with dimensionless variables. Okay, and essentially what you have is Navier-Stokes on the left with a bog standard Reynolds number, okay, and then you've got this standard forcing on the right, and this Reynolds beta really is a Reynolds number because beta has the dimensions of an inverse viscosity. So that is like UL over viscosity. Okay. Okay. So we're going to consider these in this particular form. Okay. So the ITT equations, they have, apart from the alpha U driving term, they have identical scaling properties to Navier-Stokes. And because, as I said earlier, here, whoops, I'm getting myself confused again, because Navier-Stokes has this alpha here, based on this invariant property, you expect Toner-Tu to have the identical thing, and indeed it does. You get this alpha, and so we're going to look exactly at time averages of this thing and see what bounds we can find. And I'm going to call for D is 2, so 4 minus D is 2 there, and 4 minus D when D is 3 is 1, and there's the 2 and the 1 for the dimension. I'm going to call these PNM, N derivatives in L2M, and these QNM in 3D. So what do we find? Well, what we find is the following. That, yes, the L2 norm, which I call H0, and the H1 norm, which is grad U squared, basically I call it the time averages are bounded very nicely, okay? And you have one more piece of information, which is very good news, that the L4 norm of the velocity field is bounded, just the nature of the way the equations come out. Okay. Now, we have no vortex stretching. We're in 2D. You see, we're in 2D. We have no vortex stretching from Navier-Stokes. So when I sat down, I thought, oh, this is a piece of cake. It's just work it through. And then to my horror, of course, I realized that then you're going to have a curl of the U mod U squared term. And that is very bad news. So, you know, that threw me into a bit of a tizwas, and we sort of sat down and worked it out. But then when you actually start looking at the necessary properties, you found that what comes to your rescue is this extra piece of good news, that it gets you out of jail. And what you can quite easily show is that H1 is bounded for all finite time, but it's an exponential bound in time, which means that although you've got a finite bound, you don't really have a global attractor. You need a finite, you need a number. Okay, now I heard rumors that somebody has solved that problem. I'm not sure who, but it looks to me reasonable that it could be done. Okay, now here, and I'm just writing them down, you don't really need to consider the numbers, but now we use U0 as a scaling parameter, choice of velocity field. The standard choice will be root alpha over beta because of dimensionality. Okay, but you don't have to choose that. You could choose U0 is nu over L. That makes Reynolds nu equal to 1, incredibly low Reynolds number. So Reynolds beta would actually be the dominant Reynolds number, whereas for this one, here, Reynolds nu is the dominant. So you've got much more in this system than Navier-Stokes because you've basically now got a much richer set of dynamics with 2 Reynolds numbers to play with. Now, what I've given you here is simply estimates on all these guys for Reynolds nu much bigger than Reynolds beta. I haven't written it down for the other way round, but you could just sit down and do it. Okay, and you'll see in the numerics in a moment. But you can basically, so any solution that you compute or write down would have to actually obey these inequalities. Now, I've had people come to me and they say, well, I have this solution and I've computed this and it doesn't fit your bound, so your bounds can't be sharp. And I say, no, you don't understand. It just means that you've got a global attractor. You're maybe only exploring one little bit of the attractor. It doesn't mean you have to saturate the bound. Okay. And this is true for all solutions. Now, here are some numerical computations. This left-hand panel here, okay, is for U0 root alpha over beta. So Reynolds nu dominates over Reynolds beta. And what you're seeing is P naught M versus time. Okay, and then this bit is just taking a little piece and stretching it out to actually look at more detail. And that's the time average of P naught M versus M. Now this one, this panel, is the other way round. This one is Reynolds nu equals 1, and Reynolds beta is something much bigger. And you can see significantly the totally different dynamics. Just, without going into the detail, you can actually just see it visually. Okay, so let's move on. Now 3D estimates you don't want to see. We only have weak solutions. But you can find all these bounds exist. And if you're going to be doing 3D computations, they basically must fit with these. It's a lot of work to do these things. But basically, this is all we have, because we haven't solved the regularity problem for 3D Navier-Stokes, so we haven't got it for this either. Okay, so let's move on. I'm now going to move over to Toner-Tu-Swift-Hohenberg, which, as I said earlier, Edgar did me a big favor by introducing them this morning. Essentially here, you've got Swift-Hohenberg, negative diffusion, hyperviscosity here, and then you've got the Toner-Tu forcing. Now, I've noticed, being an outsider to this, but reading the literature, some people take a positive thing here and others take negative. I don't know why, but in the previous slides I've had a plus alpha, in this one I've got minus, but it doesn't really matter. Okay, now if we do the dimensionless version, as before, it dimensionalizes exactly to 2, in effect, here and here is anti-diffusive Navier-Stokes, here is your Toner-Tu part, and now here is your hyperviscosity. And we have 3 Reynolds numbers. Reynolds gamma naught, which is your standard Reynolds, Reynolds beta, which we've discussed before, but now I've got this coefficient, and I call it Reynolds gamma 2, and it's Reynolds gamma naught times the inverse of this, which is the ratio of the viscosities. And this is important, because in the next few slides, and in the numerics I'm going to show, this is the guy that actually appears. That's the natural Reynolds number that seems to be important. Okay. Now, I'm not going to do all the details. The fact that you've got a PDE like this and you have hyperviscosity means that all the stuff on global attractors, etc., goes through like a dream. It's not particularly difficult to do. You just do it. And so, let's just digress. What I want to do, if I go back, that since we have a global attractor, what I want to do is see if we can estimate its Lyapunov dimension. Okay. We're in 2D. Okay. We're going to just do to 2D. Now, those of you who are old enough, like me, will know what the Kaplan-York formula is from dynamical systems. And Kaplan and York came up with this idea There was originally for ODEs, but doesn't matter. You have a set of exponents whose growth and contraction of volume elements in the phase space. And you sum the exponents, and essentially it says this. You sum the exponents up to a certain point, and it's positive. You add one more in, and the sum turns negative. Okay, here. So you've got some n0. So say your n0 was 199, and your sum over the first 199 was positive. You add the next one in, the 200th, and the sum turns negative. It's that n0 that basically bounds above your Lyapunov exponent from this particular formula. And so
how do you order these? I mean, what do you mean by the first 190 and the first n0?
Well, how do you order them?
Maybe I'm missing something obvious.
You have to do Gram-Schmidt and all that. Get order them by size. Yes.
By size.
Yes.
Okay.
Yeah.
That's all.
Yeah. Okay. Now that basically was for finite dimensional phase spaces. Constant and Feucht in 85, they reworked the whole idea because now you're in an infinite dimensional space, a global attractor for a PDE. And I'm really summarizing in half a page, a really big paper. But essentially they said this: you take volume elements of some sort, okay, you have a solution U, you perturb it by delta U, you form volume elements in this form, and then what you do is you take your PDE, you linearize it and find the evolution of the delta U. So this M is an operator from your PDE. Okay, and when from this and from this, you of course find that Vn is an exponential of the integral or the time average of this trace. And that trace is defined essentially, now you're in a Hilbert space, you're spanning your attractor by orthonormal functions phi, because you can do that. You're in, if this P is a projector, so you're projecting down onto these orthonormal functions. So that's what that means physically, mathematically, and that is interpreted as the sum of the first n exponents. Hello.
So M can be non-normal. Why would they be orthonormal necessarily?
Sorry, what do you mean?
Your M, your linearized operator can be non-normal. So
I'm just going through a process of this is really a Navier-Stokes thing that we're doing.
Well, Navier-Stokes linearized can be
In effect,
non-normal.
in effect, yes.
But you just said that phi's are orthonormal. Can you always select those? To be
Yes. Yes, you can.
At least in this
Yeah.
case we can. There was shear, etc.
Okay, so now you don't want to see this calculation, but there are two big pieces of artillery that you want to bring. Well, before that, first of all, the trace of the negative Laplacian is simply this, which is very nice. These things sum up to n, but then two bigger pieces of artillery. In 1985, Elliott Lieb and Walter Thirring basically proved these very beautiful orthonormal inequalities for these phi's. I think 1985, nobody dreamed that there was anything new to find. But in fact, this really is true, and this is the dimension. So we're interested in D's too, so this is squared. And then Peter Constantin in 87 showed that functions whose gradients are orthonormal, basically the estimate is logarithmic. Okay, now, many pages later, where you use these two big pieces of artillery, and you get an estimate for DL using these, and we find that this Reynolds gamma 2 to the 3/5 with a log correction, beta and alpha R are in there, but it's very insensitive because it's a 1/5 power. So Reynolds beta is in there, but it doesn't really matter. In a sense, it's this Reynolds gamma 2, which is the And so this Reynolds gamma 2 to the 3/5 is the estimate we find. So we set about doing a numerical program to see if we could basically find that 3/5 estimate. And the previous work on the previous slide and this has been done in this program. Okay, now you go back to as far as 91. Grappin and Leorat started 2D Navier-Stokes. It was very limited, of course, because their computational power was very limited in 1991. And they essentially set about trying to estimate the 2D Navier-Stokes attractor dimension numerically. Okay, but there's been a lot of work since, particularly these two papers, which we followed. And in essence, what we find, as Rahul said on the back row, you have to use a Gram-Schmidt process. What we find is this. You see, DL versus gamma 2, and this, it isn't written on the slide, but is indeed 3/5. We actually do see 3/5, exactly like the estimate. Okay, now there are many hundreds of exponents. This is a much bigger calculation. It took quite a long time to actually do it. And this is the sum of the positive exponents, which I think is an upper bound on the Kolmogorov-Sinai entropy. Okay, so basically the numerics and the analytical estimates actually fit. Now what does 3/5 mean? Well, 3/5 in effect means that if you're computing numerically, you're in 2D, so you need Reynolds to the 3/10 in each direction as a resolution scale. Okay, so how am I doing for time? Good, yes, I'm doing fine, aren't I? Okay, well that was the second part of Gall. So now the third part of Gall, okay, this is for the phasers in the audience. So having done what I've done, I'm basically showing you what analysis can do for these equations. Now I'm going to show you what it can do for Cahn-Hilliard Navier-Stokes. Okay, now those of you who've worked on this exactly know this model. A phase field model, phi, where you're looking at positive phi's and negative phi's in the heavier phase. So here you have Navier-Stokes coupled to a chemical potential mu, an Atwood number, basically that's the gravity, okay? And now here is the Cahn-Hilliard part, okay? And your mu chemical potential is delta F by delta phi, and we've seen this written down many times during this slide, during this conference. And here you've got the Navier-Stokes part, so you've got the fluid energy in here on the right. Okay, so what can we do with this? Okay, well, it came as a surprise to me that when I started working on this, particularly on the Celani paper, working things through, how I was amazed, you know, I started to find out dE by dt, and I got pages worth of algebra, and I thought this is never going to work. And then I found it all cancelled or integrated away, and thought, my, these guys are good, because you simply get dE by dt is this positive energy part here. It's really very, very pretty. And there's a big, obviously, there's a big literature on this. Now in 2D, Charlie Elliott and Sung Mu in '88, just for Cahn-Hilliard alone, not Navier-Stokes, proved that Cahn-Hilliard is regular. But 3D regularity properties are open, not solved, okay. But then 2D Cahn-Hilliard Navier-Stokes has been shown to be regular by both Abels and Gall and Grosselli. They did different boundary conditions. So it follows, in a sense, 2D Navier-Stokes is regular, as is 2D Cahn-Hilliard. You put them together, and yes, it's regular. 3D Navier-Stokes, it's an open problem. 3D Cahn-Hilliard, it's an open problem. You put them together and it's even worse. Okay, so if it's an open problem, can we say anything at all about it? How if you're, say, computing it numerically, how do you know that you've got solutions under control? Okay, and this is the way that basically CFD people do it, and this is a digression. Okay, it's what's called the Beal-Kato-Maida theorem for 3D Euler. It was 1984. Before that, people knew pretty much nothing about Euler. But this theorem says this: you take Euler, periodic domain or an infinite domain, you take some initial data, and then you say, suppose there exists a solution on this interval, T star, up to but not including T star, where T star is the earliest time that the solution loses regularity. So you start with a nice solution, it gets to be rough, and then you lose regularity at T star. It says, then at T star, that integral must be infinite. Okay. Now, what are the conclusions? It looks a bit strange. There's a converse to this, that if your integral of omega infinity is always finite, then you've got control of your solution. Now, there is a consequence of this theorem. If you're a smart guy in the back row and you have your own Euler solver, and you say, right, I've just shown that Euler, omega infinity, the maximum of the vorticity, blows up for, say, p is a half, for instance. That's your result. Then your result is wrong, because the integral of anything that's minus a half or less than 1 is actually finite. And so you've got a numerical result that has actually violated this theorem, and it's telling you that your code basically is suspect. Okay, and so anything that you think has gone singular must have p greater than 1. Now, what I'm going to show you, and I'm actually almost through, what I'm going to show you is that we can prove a very similar theorem for 3D Cahn-Hilliard Navier-Stokes. Okay. And essentially, you do it this way. You take the energy, E, like so, and there is your half U squared. Now, this is like these objects in L2, 2, 2, 2. Okay, so I'm going to define E infinity, basically based on this LP norm, based on that. This thing is P is 2. So I'm going to define E infinity as that thing with infinity in place here. Okay, and then our theorem basically is exactly like the Beal-Kato-Maida theorem. It says, suppose there exists a solution up to, but not including T star, where T star is the earliest time it loses regularity, then the time integral of E infinity must be infinite. And if that object actually is finite throughout your integration, then you know you're okay, you know you've got control of your solution. Okay, now of course, these guys, L infinity norms are notoriously difficult to get accurately numerically because you might be falling in between points. Okay, so the only way we could think about that is essentially to do this now in LM. So that's this P, I'm going to put P equals M. Okay, and then we basically looked at the data that we had. Now this was 2016, so the data isn't as good as it maybe could be 8 years later. It really needs redoing. And we did M is basically 2 up to 6, and you actually find it's not blowing up, it's actually turning over there if you carry on a little bit. So it actually is under control, the EM is under control, and you would like to go much higher, of course, to get close to something big, but we could only do up to 6 at the time. I'm sure now one could do actually quite a bit better than this. Okay. And in effect, this is a plot. Isosurfaces are phi. Okay. Isoplots are 2 phi 6 cubed as it actually evolves. And this is really the Rayleigh-Taylor instability, where you see these mushrooms. You know, if you know anything about Rayleigh-Taylor, you get these bubbles going upwards, and you get spikes going downwards. And although we can't really see the spikes in this because it's dark, you do indeed get them. And here are the sort of mushroom bubbles, very typically of Rayleigh-Taylor. Okay, and that's it, 15 minutes early, 14 minutes early. Thank you.
Thanks a lot. Wonderful talk. Time for questions. Don't be shy.
You showed their estimates, which is upper bound, and then numerically they are matching. However, we know that from the classical work on the dimension of the attractor, there is a work in which showing that the upper bounds are sharp by establishing lower bounds rigorously.
Yes.
Did you try to attempt to establish rigorous lower bounds?
I did.
Parallel to yours?
I did, and I failed miserably. Sorry.
We can ask Idris for help.
I'm not young anymore. So.
But I ought to say, as an analyst who came into this late and started looking at Cahn-Hilliard Navier-Stokes, I kept saying what a beautiful system it is. It's really nice. Okay.
You gave us 3 examples of equations.
Yeah.
Of course, you know, there's many more that you could possibly cook up. So, is there some kind of general conclusion?
Well, in a sense, we're lucky here in that the Toner-Tu has the same scaling properties as Navier-Stokes, and Swift-Hohenberg almost has. And in that sense, it tells you what to pick. It mimics the sort of Navier-Stokes, all those time averages. So if you handed me something else and it didn't have those scaling properties, I'd be up the creek. You'd have to work really hard, but it probably could be done. Yeah.
May I make a comment?
Yeah.
I mean, you know, physicists come up with an equation a day. One is active, the other is non-reciprocal, and so on. And it's good to know that there are mathematicians out there who can at least tell you what is known in those equations. So it's a message both to mathematicians and to physicists. Talk to each other. There's a lot of things to uncover.
Yes.
Yeah, maybe on that note, I have a general question. You have your 2D Navier-Stokes, you have global regularity because of the absence of vortex stretch, essentially. And then you have the 3D there.
Can you speak up?
Yes. So you have 2D Navier-Stokes, you have global regularity because of the absence of vortex stretching. And then you have the 3D case where it's an open question. Now there are many systems which are somehow in between, either through a strong rotation or any other type of symmetry breaking. Is there anything known on, let's say, a transition between those two systems, or is there any way of attacking this analytically?
Well, Idris's work on the primitive equations, which in some sense, in 3D, you take 3D Navier-Stokes, you put in rotation and temperature, and then for the primitive equations, because in the atmosphere in the ocean, dW by dt, the acceleration is so small that you drop it. And then Idris has shown that those are regular. They have very, very beautiful properties. So that's a sort of halfway house.
What John is meaning is basically think about hydrostatic primitive equation.
Okay.
So it's a 3D, but the vertical momentum replaced by the hydrostatic balance. So it's a 3D with a full field and still global. Actually, what's interesting, their story to...
No, carry on.
In the viscous case, it has a global regularity. In the inviscid case, like Euler, it blows up in finite time. So it is better than Navier-Stokes and worse than Euler. Does this answer you? This is in between?
It's in between, yeah. But
Two-dimensional in between.
yeah. I was wondering if there are other results that where you can interpolate.
I understand what you're saying.
Yeah.
So even coupled with CH equation, the physical meaning of the non-linear term is still vortex stretching. Is it correct?
Yes, it is.
So, which means if you have different regularity, the term changes the way of how vortex is stretched. Is this correct?
I'm really not sure. I mean, when we do Cahn-Hilliard Navier-Stokes and you have Navier-Stokes on the left, your left, the vortex stretching, of course, comes from the curl of the u dot gradient term. So that's still there in Cahn-Hilliard Navier. So I think it really is real fluid vortex stretching.
Yeah.
And then the other nonlinearity is you've got the Laplacian of the phi cubed minus phi, which is the Cahn-Hilliard part, and then you put those two together, and that's really bad news.
See no more questions, and let's thank John again and all the morning speakers.